So let me get immediately to my first presentation. So I will take you by hand more or less through the solar system, and I will show you, because I have a European bias, the European missions that I know by heart. But obviously, I will make mentions whenever is required and needed to the large number of missions which have been carried out by NASA and other international partners. However, let me say that in Europe can be very proud that basically of having achieved the incredible thing of basically spreading European-made hardware all over the solar system with a budget that at NASA headquarters, as Karen McBride can confirm, is enough just to carry out a few studies. What is this budget? Well, in the science program, historically, we have something like oscillating, depending the years, between 300 and 400 million a year. Obviously, we got to pay for the infrastructure, we got to pay internal taxes, etc. So we have a purchasing power, a cash flow every year of 300 million. And this is shared among 3 disciplines. Well, in NASA, they are 6. In Europe, we keep the sun and the space nearby the Earth and the planets all together in one single discipline. So, and I was, for a long time, if you allow me, the king of this huge domain, going from the high atmosphere up to the outer part of the solar system. And so, the exploration in a broad sense of the solar system has spent in the last 20 years about 150 million a year. So you are accustomed to the NASA budgets, and you can tell the difference. Basically, there is a factor 8 different in the cash flow. But we only have a factor 2.5 less missions. So I'm kind of proud of the European system because, well, when you don't have money, you got to use brain and you got to be smart in order to achieve what you want to do. Because if you wait from gifts from the sky, particularly in this continent, they never come. So we could wait forever. So let me take you, after this small introduction, to where this 150 million has taken us. And everything started with a mission that is very close to Cesare's heart and my heart, that is the Giotto mission. So while in Russia and in the United States, they were fighting in space in order to conquer the moon, and obviously it's well known, NASA and the United States got there first and put the American flag on the surface of the moon. In Europe, we were moving the first shy steps into space. So in the same time frame, while there were a large number of missions abandoning the Earth's gravity and going to the moon, just before the Giotto mission that was launched in 1985, if I remember correctly, it was the first European-made piece of hardware that abandoned the Earth's gravity. So you may understand how late we started. Basically, we started 20, 25 years later. Even if in Europe, not many people know that, but the second ever satellite to go in orbit was a European satellite, was an Italian satellite. You wouldn't believe it. In Italy, we always have peaks, and then we don't follow. It's the history of this country. But anyhow, we started so late, to the point that when I joined ESA in 1987, I was working under an instruction of the highest advisory committee of the agency that was saying, because the exploration of the solar system is too expensive and too complex for European industry, ESA will limit itself to orbital mission and specifically to plasma physics missions. So when our common friend, the first medical or the second medical director of the science program, Roger Bonnet, called me to organize a program of exploration of the solar system, and I said, but thanks for having hired me, but I cannot do it, because either we violate this basic rule of the agency or we don't do anything. And he said, come on, Marcello, you know, everybody knows you. You don't respect the rules, so that's why you're here. Well, that was true. I couldn't care less about that recommendation. So we started working very, very intensely in trying to put together a program. And Roger had the great merit at the time of having laid down the first long-term program for Europe that was called Horizon 2000. We were in the 80s, and so we were thinking that by year 2000 we would have been able to accomplish a large number of missions. More or less we made it, probably with 10 years delay, but you know, it's what you call contingency time when you do space missions. There's a lot of problems here and there. But anyhow, since then, basically we have European satellites observing the sun, orbiting the Earth for plasma physics missions, of course, going to Mercury very soon. We reached the moon, better late than never. Together with NASA, we went to Saturn. We are still in orbit around Venus and around Mars. We reached comets, so we are reaching comets. We've flown by asteroids. So, well, you name it, we've done it. And I underline, again, with 150 million a year. So here is planet by planet what we have been doing in the last 20 years or so. Some of the missions are purely European, so some of the missions are in collaboration with international partners. So the color coding is that ESA is white, confirmed collaborations in yellow, and possible collaborations in red. So when it comes to the space nearby the Earth, we have two major missions. One is SOA and Cluster. They are still operating despite the fact that they are extremely old. They are almost 20 years old, this mission. It's a long story. SOA is in collaboration with NASA as well as Cluster, but all the hardware basically was built in Europe, apart from some of the experiments. As usual, we have the money for the missions. We don't have the money for the launchers, and so we had to negotiate. And thanks to Mama NASA, that has become a kind of launcher supermarket in the last years. ESA has been able to launch its satellites until we had a more reliable Ariane 5, which is not that reliable, and I'll tell you what happened. For instance, we launched Cluster twice. Cluster is, as the English name says, is a cluster of satellites that are basically in the cusp of the Earth magnetosphere. We'll see the details later, but let me tell you this anecdote. So we wanted to save money because we don't have money, so you gotta save. And so we decided, we're so smart, we're going to launch this mission on the first prototype of Ariane 5. Obviously, the first prototype of Ariane 5 was given to us for free, and naturally, it exploded on the launch ramp. And you wouldn't believe it. We collected the satellites in the mud of Guyana. And the mud was very good because it absorbed most of the shock impact, the shock waves during the impact. And we realized that a large number of the experiments, once they were cleaned up from the mud and the water, were still functioning. Well, you wouldn't believe it. There was the British delegation. We are organizing delegations, a kind of the boards of the directors where we have the national representatives. They pay the money, so they are in charge. That's understandable. When you pay, you want to be in charge. And you wouldn't believe it. Instead of giving us, encouragement and say, it's not your fault, you're going to make it again, we support you, they said, we notice, with a very strong British accent, that some of the experiments are still functioning. This is a typical example of over-design. It means that you're wasting taxpayers' money. Well, my reaction was in Roman and cannot be translated. Anyhow, we survived everything. And again, to save money, eventually we launched on two satellites on one and two satellites on another one, on two Russian launchers. And they were successful. They are the Soyuz launchers, the most reliable launchers ever built by mankind or humankind. And by the way, nowadays are the only launching system that will allow American astronauts to go to the space station. So life is funny. After so many years, America relies on Russia. That's okay. It's nice when we do things in peace. So it's a grandfather of the missions. It's observing the sun. I will show you the things. Messenger is a U.S. mission. We have just a cultural scientific collaboration. They started later, and they have already reached Mercury. That is the difference of having huge budgets, of having small budgets. We got to spread the budgets over a long time. But Bepi Colombo, which is a famous name here in Padova, will be launched in 2013, 2014. It's a 2013 launch window with a launch in January 2014. It will go to Mercury. It's a gigantic mission. You will see the detail later. And what is funny, by spending only 100 million on a moon mission, I've been able to put together a lunar program. And that was almost hilarious. By doing what? Well, I opened the first time the collaboration to China during the period when most of the states, of the governments, were under prohibition of collaborating with or even talking to China. So we said to ourselves, you remember what Bonnet said, Marcello breaks all the rules. And I said, well, that applies to government. ESA is not a government, and we talk science. We don't talk politics. So I'll go talking to the Chinese. And we had the first hardware collaboration with China ever in the history of space. Then I decided to collaborate with the Indians on Chandrayaan. And basically, we gave most of the experiments on Smart 1 to both the Chinese and the Indians. So by paying 100, we found Europe flying 3 times around the moon. We keep talking about Italian, German, British missions to the moon. Still waiting. We'll see what happens in the future. The other planets. Venus Express. Venus Express was another invention out of the magician hat. One day, Roger Bonnet came to me and said, you wouldn't believe it, Marcello. We made a financial assessment at the end of the year. We got a surplus in the budget. I don't want to give the money back. Do you have any ideas? And I said, well, when it comes to spending money, no problem, my dear. I can find a mission immediately. So first thing that I did, I went to, it was the second meeting of, how's it called, the MIPAG, Mars Exploration, Planning and Analysis Group. And I said, I always loved Mars, and I wanted to do, at that time, a second mission to Mars for Europe. So I went there and made a presentation in front of NASA managers and the NASA scientists by saying, I got a satellite and the money to launch it. I need collaboration for operations and a payload. Are you guys interested? Well, what do you think the answer was? The answer was, oh, come on, what you talking about? ESA will never be able to go another time to Venus. You are telling us lies. A more polite NASA manager told me, oh, I think this is a long shot. I didn't talk to the guy for about 5 years. And eventually, I launched the spacecraft, not to Mars, but to Venus. And so we went there, and we're still there. Out of absolutely rage with NASA at that time. Meanwhile, we had launched Mars Express, and the reason why we could launch so quickly and so cheaply, imagine, Venus Express cost us less than 100 million. Why? Well, you must have heard, maybe if some of you is a space freak or a space lover, some years ago there was a NASA administrator that was talking about faster, cheaper, and better. We do more mission with less money and with augmented scientific results. Well, we're still waiting for these missions from NASA. The administrator eventually retired, and the philosophy was never applied. However, there was something good in these ideas, but probably NASA didn't really find the trick to apply the idea. And again, because we don't have money, we got to use intelligence. And so how did we make the faster, cheaper, and better in Europe? We had a gigantic mission, gigantic for European standard, the Rosetta mission, which is still flying its long way to reach the comet. And we invested 650 million euro. For us, that's a gigantic budget on the development of that mission. And we realized that basically what characterizes missions into the solar system, it's the goal. It's not so much the difference in satellites. Basically, you need a 3-axis stabilized spacecraft, you need a propulsion, you need computers. Basically, the heart of every spacecraft is always the same. So the idea that the head of the engineering department and myself had is, why don't we take all these subsystems that we have as a spare after the construction of Rosetta, and we reassemble it in such a way that we can build a spacecraft for a small amount of money. And that we did by saving a lot of administration, because once you have all the hardware already tested and developed, you don't have to go through several invitations to tender for industry. You don't have to do through long and exhaustive qualification tests. You can jump directly into the construction phase. And so that we did, and that allowed us to make Mars Express for 150 million. And then because we had the spare of the spares, we put them together for Venus Express. And so that allowed us, with less than 1 billion, to make 3 missions to 3 different planets of the solar system. And now we're doing the same. Bepi Colombo was the precursor of Bepi Colombo was Mart, where we tested the system of navigating with the ion propulsion. It's a very different way of controlling a spacecraft. Why? Usually a spacecraft is coasting. It's like a car that goes downhill, right? Because we don't use motors in deep space. Propellant is too heavy and too expensive. So we get the momentum, no frictions, we keep the momentum, and off we go, and then we use planetary assistance, what Mother Nature's allowed us to use, to go places. But when you use a plasma or an ion drive, you have a very tiny thrust, una spinta molto leggera, tiny thrust, of the order of millinewton, or micronewton even. But you can keep the motor on for years and years and years. Eventually, when you integrate the small thrust over a long amount of time, you have a total thrust which is bigger, much bigger than that is produced by a chemical engine. And by doing that, you can achieve very high acceleration, very high speed, and shorten the time. Why you shorten the time? Because you're not obliged anymore to navigate along the classical Keplerian orbit. You can take little shortcuts. You can take arcs of hyperbole, which are much more energetic, but much faster to change your energetic state. And so by doing that, you shorten the cruise time of your missions. So we tested this system with Smart 1. We are implementing it on Bepi Colombo, and then we're cannibalizing the subsystems of Bepi Colombo, which goes to Mercury. It's a very hot place. For constructing Solar Orbiter, which goes very close to the Sun. It will be the first satellite to orbit the Sun, because all the thermal requirements are the same. So a second time we're making a construction chain, saving a hell of a lot of money of the taxpayers. One of the major missions we ever seen, and I must say, as Europeans, we must be proud that we each hiked the Cassini satellite to Saturn with the Huygens probe. And so that allowed us to go to the outer part of the solar system, and according to the European tradition of navigators and discoverers, not Cesare, he's not a good navigator, he's a good astronomer. But in Europe there are many navigators. They discovered the world, and now with Huygens we landed for the first time on a new world. So we keep up the tradition. And on top of that, we have a large number of missions, because this is the European tradition, at least between the 70s and the 90s, when I almost put this discipline at sleep, and many people in Northern Europe didn't like me. Remember, one day I was there to present the program, and I said, the age of plasma physics around the Earth is over. And I didn't realize that 90% of the science community I was talking to was only able to do that. So I said to myself, sometimes you got to bite your tongue and be more diplomatic when you give public presentations. But anyhow, apart diplomacy, I was right, in the sense that the new plasma physics today is the interaction of plasmas with non-terrestrial magnetic field, is the interaction of plasma with other planetary bodies than the Earth. For instance, studying the evolution of Mercury, which is totally embedded into the solar plasma, very energetic plasma, to the point that the bow shock of the solar wind can even penetrate the Mercury surface. This is something fantastic. This is innovative science. I used to make jokes instead that some of the old-style plasma physicists, they get excited if you put a coffee pot in the deep space and you measure the interaction of the vapor of the coffee with the solar wind. It's a plasma interaction, but not that interesting, you know? So you want to do plasma physics in order to understand the evolution or the impact of the plasma environment in the solar system during the formation of the solar system. This is a major amount of science that I contributed with this mission to launch in Europe as a new science. And I don't want to go through all this mission, but just to let you know that This is a typical European activities because it doesn't cost much, can be carried out with small satellites, and is affordable also to small countries or small national agencies instead of a big agency like ESA. Because despite the fact that I keep saying that we are very poor, after all, we are number 2 in the world, even if we have a factor 8 less budget than NASA. So this is some details about the SOE missions and the cluster mission. It's very important to study the behavior of the sun. SOE contributed to really, it's a landmark because it's still alive and functioning in understanding the structure and the behavior of the sun. And once the sun emits the solar wind and the solar wind impact on the terrestrial shields, magnetic shields, it's very important to understand, first of all, the mechanisms that generate the solar wind, and then the interaction of the solar wind with the terrestrial magnetosphere. The real issue is that I remember when I was studying physics, when the professors were giving me example of an isolated system. In physics, you always have isolated systems, so that makes the boundary conditions much simpler, right? And so they were saying more or less an isolated system like the Earth in the solar system. There's nothing more wrong than that. The Earth is not an isolated system, and these graphs shows you how much the Earth and the Earth magnetic field interacts with the sun and the outer space. Consequently, from this point of view, we are not an isolated system at all. And I'll tell you more. Look at this. This is a little cartoon that was made many years ago by Luis Lanzarotti that explains how much the Earth is not an isolated system. Forget for a moment what happens above the terrestrial atmosphere, but let's go down, and sometimes even to the surface. In the event of major solar flares, tempeste solari, solar storms, you have an overloading of charged particles on the field lines of the magnetic field of the Earth. And like everything, like every short circuit, if you have a big conducting structure, for instance, a pipeline which is made of metal, that puts together the field lines, you can have short circuits. And these short circuits perforate the pipelines. All the oil companies know that, and that's why they continuously ask for space weather forecast, le previsioni del tempo astronomico. Because fixing pipelines is very expensive, and it's more expensive when you have lots of loss of oil. So this is just one of the many examples. If you have a pacemaker during a solar storm, you better don't walk too much exposed. You better stay in a Faraday cage. In other words, stay home in a new modern house. Or everybody uses GPSs. In these days, we have continuous information, or at least if you belong to some clubs, you got information on the internet. Be careful, solar storms, perturbations to the GPS system. Why? During a solar storm, the solar wind pressure increases dramatically, and the GPS satellites are displaced. Being displaced, they lose resolution. And sometimes they even lose the signal. It was funny some weeks ago, thanks to my GPS, I don't get lost only in Padua. I even get lost in Los Angeles, where I live in these days. I got lost. The GPS kept saying, turn right, turn left, turn right, turn left. And I said, what the hell is doing? I mean, there must be something wrong. I turned the radio on, and they say, gigantic solar storm perturbing the GPS. Oh, you should have told me before. So you see the manifestation of the interaction of the sun with our planet in many, many different ways. The Bepi Colombo mission to Mercury. First of all, why we entitled this mission after the Padova professor Bepi Colombo? Well, Bepi Colombo here is a picture where he's drawing orbits. Is basically one, if not the father, of the planetary swing by for satellites. It became famous many years ago when during a presentation of the NASA project for the first mission to Mercury, they presented the mission. It was the Mariner 10 mission. by saying we will succeed to make one single flyby of Mercury. But Professor Colombo knew very well the theory of resonance and the spin-orbit coupling of a planet with the Sun. And so during the presentation, that was his incredible capability. Basically, he made computations on the back of an envelope. And at the end of the conference, he raised his hand and with a strong Padua accent, he said, "I do believe, gentlemen, that you're wrong." Total silence in the meeting room. And he was right. They were wrong. Mercury 10, thanks to his computation, came back 3 times close to the surface of Mercury, and so the mission was dramatically improved. Since then, it became, the technique of studying the resonances of planets and the orbits became a normal practice for determining the orbits and the mission scenario of deep space missions. But why studying Mercury? Well, this graph is very misleading. We studied, even in the elementary school, at least some years ago, that Mercury has the highest density. Well, if you plot the density of Mercury, it doesn't have the highest density, so how it comes? As you see, Earth and Venus have a higher density if you just measure it like this. The higher density of Mercury comes when you take into account the so-called uncompressed density. What is the uncompressed density? If you can read, is the average density of any material that any material would have at zero pressure. In other words, if we take the material that composes Mercury and we don't take into account all the pressure of other materials compressing Mercury, the density of that material is much higher than the density of the other materials that form the Earth, Mars, Venus, and all the other terrestrial planets. So this is very interesting for 2 reasons. First of all, because such a high density compared to the overall structure of the planet, such a big nucleus of a high density, has given Mercury itself a very high dynamical stability. Indeed, because of its stability and its coupling with the gravity of the Sun, the spin axis of Mercury is the only spin axis of the solar system that never moved a little, has always remained totally perpendicular to the plane of the ecliptic. Thanks to that, Mercury, that has the hottest surface of the solar system, has the coldest poles of the solar system. Why? Because they have never been illuminated by the sunlight. And on top of that, there is even the chance that on the poles of Mercury, we could find primordial ice. Because if you have cometary impacts on the poles of Mercury, the poles are always at night, and they are thermalized to the cosmic temperature. And consequently, in the hottest planet of the solar system, there is a chance of finding in the poles the oldest ices of the solar system. But even more important is that Mercury is an end member of the solar system. And if we want to understand how the terrestrial planets and the rest of the solar system evolve, we got to put boundary conditions. And so by studying Mercury, we can have boundary conditions on the formation and evolution of the solar system. But as far when it comes to our planet, it's even more important understanding the behavior of the atmospheres. We keep talking in the last years of the greenhouse effect, l'effetto serra, so the global warming, il riscaldamento globale. What is that? It's nothing else than what happened on Venus. Actually, the real proof at planetary level that a greenhouse effect at a global scale does exist came from studying Venus and not from studying the Earth. We have so much emotionality when it comes to the Earth that one day I found on the scientific journal Nature 2 papers, one in 2 facing pages. One was saying global warming does exist. The other paper was saying global warming does not exist. This demonstrates that even scientists can handle in completely different way the same data sets and come to opposite conclusions. Nobody ever disputed the fact that the greenhouse effect on Venus is extremely effective and could be a possible evolution of the atmosphere of any planet. So what is interesting is when you look at the so-called effective temperatures, which is nothing else than the temperature of a black body, of a body painted black, okay? Don't think of Planck or stuff like that. It's a simple painted black body that you put at the same distance from the sun of Mars with the same dimension of Mars, distance of the Earth from the sun with the same dimension, and so on and so on. You would have much lower temperatures than what you can measure on the surfaces of the planets. Why? Because you have an atmosphere. So the atmosphere elevates dramatically the temperature of a planet, on a normal atmosphere. But then, if you have continuous injection of so-called greenhouse gases into the atmosphere, the temperature can keep increasing and increasing, which is exactly what happened on Venus. Basically, the situation on Venus is like what would be on the Earth if you let all the oceans of the Earth evaporate and transfer to the atmosphere. You would have a very dense atmosphere and a catastrophic greenhouse effect. And the temperature of this planet would raise probably to something like 500 or 600 Celsius, which is basically what has happened on Venus. We don't know if there was a migration of waters from the surface to the atmosphere. We know for sure that basically all the volatile produced at the formation or given to Venus at the time of its formation basically are now ejected into the atmosphere. And the funny thing is that we keep talking about CO2, forgetting that there are other gases that are extremely effective for raising up the temperature of a planet. And one of those, it's very familiar and not noticed at all. It's water vapor. Water vapor is the one, CO2 raises the temperature, is the gas that triggers the greenhouse effect. But if you have some humidity, then you start evaporating. You start transferring the humidity from the surface to the atmosphere. And you see that the temperature increases thanks to the H2O in the atmosphere. And then you have sulfuric acid. On Venus, we have sulfuric acid. On Earth, you might have different compounds created by pollution, which raise even more the temperature, up to the levels of Venus, 500, 600 degrees. So you see, playing with greenhouse effect can be extremely dangerous. Obviously, we are just at the beginning of the process in this planet, but the problem is that it's a feedback mechanism, and it's a very complex mechanism, and we don't know the interplay between the many different variables. It might happen that you touch a variable in a very unstable system, and you have a catastrophic feedback effect. We don't know yet if that is possible or not. So that's why we should be careful if we care about our planet and about ourselves. So this is a great support that planetary exploration can give to understanding of our planet. I will go quickly about the atmospheric effect. What is interesting on Venus is when on a planet you don't have an ocean, instead of having perturbations that are limited to the northern hemisphere or the southern hemispheres, and you never have meteorological fronts crossing the equator, on Venus, because of no discontinuity created by the presence of oceans, you have, at least on the high atmosphere, a kind of a ribbon type of perturbation that goes from the North Pole down to the South Pole and vice versa. And this has been confirmed with observations carried out by Venus Express in many different wavelengths. SMART, as I mentioned, is the tiniest, the smallest mission that ever went to the moon, but it's has been really a concentration of high technology. The little camera that you see here, some of you have been working with Rosetta cameras or Mars Express cameras, etc. These are very performant, bulky cameras. This one has 1.5 kilograms of weight and had a resolution of 100 meters from 100 kilometers. So imagine your Nikon or your Olympus is as heavy as this camera on SMART, but it has a resolution of about factor 10 to the 4th less. Okay, we're using the atmosphere, so maybe 10 to the 3rd less for a mass which is the same. So this is just one example of the amount of technology that we put into this mission, but I will show you later. Another interesting issue, and important for understanding ourselves, basically, is the mechanisms that generated life on our planet and why life was only generated on our planet and not on other planets. Well, you must have some boundary conditions. You must have a source of energy. You must have a source of carbon. And on top of that, you must have climatic, environmental stability. For maintaining life, actually creating prebiotic molecules is simpler than what we believe. But they are easily destroyed in planetary environment that don't have a long stability. And when I say long stability, at least of several tens of million years. And apparently this was the case on our planet, but was not the case in other planets. From a purely thermodynamical point of view, if we extrapolate from today's experience, there is an habitability zone in the solar system which is bigger than the Earth. And it almost reaches today even Mars. So why Mars appears to be so void of life? I think that we have to look back and see what are the theories about formation of life on our planet. There are two basic theories. One of I said you need a source of energy. If you have thermal sources at the bottom of the ocean, you have the energy, you have the environment, the water, and you have the stability. And you have the protection against the radiation from the sun. The same effect can be created in a primordial phase when the sun was still building up and was much colder than today, about 30% colder than today. So the Earth was totally covered with an ocean of ice, similar to Ganymede or Europa on Jupiter. And under that lake, you have a very stable, very protected environment, a bit cold, but life don't care about too cold or too hot. It really cares about stability and protection against ultraviolet radiation and ionizing radiation. So nothing better than having such a situation to build up life at the bottom of the ocean or under the ice cap. And apparently this situation never happened on Mars. So maybe this is the reason why we don't find much, but we keep looking, of course. Another consideration is that when we look at the evolution and we compare the geological evolution of Mars and the Earth, on Mars, the time when maybe the conditions were stable enough and humid enough to develop life were much older than the Earth. Why that? Well, the only justification is that Mars is smaller and evolved and cooled down and evolved more rapidly than the Earth, even if the formation takes place more or less at the same time, according to recent theories. The dimension of the body determines the cooling procedures, the cooling aspects of the planet, and if I cool down more quickly I can develop conditions for having water on my surface. But then the water disappeared on Mars for some reasons, and we're studying that. And so theories for the time being place the habitability, the possible habitability zone on Mars well before what happened on Earth, at least 1 billion years before. How do we look for humidity and water on Mars? With Mars Express. This is the apple of my eyes. It's a mission that I invented myself, I must say. And I'm very proud to say that the penetrating radar that carries is the first penetrating radar ever on a satellite. And it's producing fantastic data. Now these data are being complemented with the data of another Italo-American radar, which is called Charade, and is flying on MRO, which is a NASA mission. But still today, we have no direct proof of presence of liquid water in the underground of Mars. Why? Well, we have a systematic possible error in the interpretation of the radargram. The real problem is that when you invert the signal of the radar, you have to make assumptions on the value of the dielectric constant of the material through which the radar wave is penetrating. And we don't have a ground truth, obviously, so the interpretation of the radar data, it's a kind of model dependent. This is the reason why, together with a group of friends and collaborators, we have decided to fly penetrating radar in Iceland in order to not only to study for the first time active volcanoes and making a prospection in depth of the active volcanoes, but also to derive the ground truth and the absolute value of the dielectric constant of ices at different depth and different temperature, with the hope of back-calibrating the data from Marsis and Sharab. So Marsis has been designed really to study the water cycle of Mars, from the depth to the surface, from the surface to the atmosphere, from the atmosphere to the dissociation in the ionosphere and loss, exospheric loss towards space. So it's a small but very coherent mission and pretty successful, I must say, and it's still flying. And it costs us $10 million a year to make it fly. And every year it's a big fight because we don't have the money to keep it alive. Cassini, still flying. As I said before, it's probably the most successful ever mission in the solar system. It's something absolutely wonderful. And the European contribution, the most evident European contribution has been the Huygens probe. But we must say that the Italian Space Agency provided this big chunk, which is the antenna. It's the first development of a communication antenna that can also operate as an active radar. And then we contributed a little bit of experiments, the visual channel for the infrared spectrometer, and pieces of hardware here and there. But obviously the hardware is basically 90% American, while the probe is 99% European. So this gives you an idea of the mission to Titan. And when you look at the morphology, I was discussing this with Maurizio Paiola today, because we were discussing hydrology on Mars and morphologies. And I said to him, when you go to Titan, you see exactly identical morphologies that you could see on Mars or you could see on periglacial terrains on the Earth. The real problem is there that the temperature is incredibly low, that the water is replaced by liquid organic material, kind of asphalt or something like that, or liquid methane, that the rocks is ice, because the rocks, it would be too cold and they would become too friable. So it's a kind of upside-down world. And so the combination of parameters, though, is such that when you look at just the morphologies, they are just like on our planet. So it's very interesting to study. And there is also the idea that in the primordial atmosphere of the Earth, the composition could have been extremely similar to the present atmosphere of Titan. So the idea is to make a comparison. I mentioned Rosetta. Rosetta also is a concentrate of technology. It's a gigantic spacecraft, including the solar arrays. The dimension of the solar arrays are more or less as long as a medium soccer field. You know, when you go playing at the church in Parrocchia, you have reduced soccer fields, more or less is the size of the solar array of Rosetta. Why that? Well, with these solar arrays, we go almost at 4 astronomical units of distance. An astronomical unit is 150 million kilometers. You multiply by 4 is 600 million kilometers. If you look at the sun from 600 million kilometers, it is much, much less intense than any of the light bulbs over here. So you confuse the sun with a star in the background. Nevertheless, these solar arrays are capable to catch 1 photon every 35 minutes, get in there, and transform it in electricity for the spacecraft. So this is a European development we're very proud of, and could have lots of application on this planet as well. So Rosetta is already flown by Steins and Lutetia. In Padova, people are very active in the study of these 2 bodies, and eventually we'll reach the comet and we'll land with Philae on the comet. And this will be the first time that any spacecraft will ever land on a comet and will analyze the materials with a miniaturized geochemical and mineralogical laboratory. But the title of this conference was The Benefits for Mankind. Apart the cultural benefits of understanding the evolution of the solar system, understanding greenhouse effect, we have also technological benefits from exploration missions for our everyday life. And now this is the test to see if my very complicated machine works. Yes, it does. Okay. So you click on the Cassini mission, and you see a number of technologies that can be used and are being used every day. So, first of all, on the MADA spacecraft, we have multi-purpose antennas, which are, after Cassini, have been developed for telecommunication satellites. You have multiplex transducers at very high frequency. Again, if we can use very easily GSM telephones nowadays, it's also thanks to the communication devices of Cassini. This is a mission designed in the 80s, launched in the 90s. 20 years later, it sounds like common technology. It was not when we developed that. We have a funny instrument which is called nephelometer, il nephelometro. Well, if you drive in the Mont Blanc tunnel, nella Galleria del Monte Bianco, you will see a lot of Cassini instruments there. What are they? Well, they measure the pollution inside the tunnel, and they stop the traffic in case of too high pollution. How do they work? It's a small device with a laser beam, filters, and the gas from the tunnel, in this case, or the gas from the Titan atmosphere, getting inside, and with the photocells, you measure the lowering of the intensity of the laser beam, which is proportional to the density of the gas. And by modulating the laser, you have different wavelengths, and consequently you have different gases that can be studied. So nephelometers are used in terrestrial tunnels nowadays, 20 years later. So now these are the benefits, just some of the very many. Let's see. In a non-Mac computer, is the right click or the left click? Let me try the right click. No, it doesn't work. Let me try the left click. It does work. Okay. And then we go to the Rosetta mission. What has Rosetta mission done for benefits? Okay, I mentioned the solar arrays, low illumination, low temperature. Talking about scarcity of oil, making savings, and so on and so on. Well, imagine if even in Northern Europe or in Northern United States or in the very south of this planet, we covered the roofs of every house with solar arrays of this type, they are capable of producing energy even at night with the lunar light. Okay? So is that a benefit or not for mankind? It's enough to use it. Unfortunately, it's not the European Space Agency that can impose the utilization of this technology to everybody. Somebody else should do it. Okay? So next time you go voting, think also about the utilization of technology. Okay? Or think of when there is a catastrophe on Earth. It's important to take care of the health of the people. And in order to take care of the health of the people, you want to do analysis, okay? Well, when you go and have your blood analysis or your corporal fluid analysis, you go to a normal laboratory, the machines are as big as this table. On the Philae lander, we have miniaturized this instrument that doctors and biologists use every day in the very rugged design shape to a level of a few kilograms for the complete laboratory. Now, instead of sending this laboratory to a comet, we can put it in a backpack of a rescue team. And you send out the doctors in the heart of an earthquake, and you can give blood, urine analysis to everybody. And it's very important to see if you are intoxicated. Okay? Again, these kind of applications are possible. It's enough to look around and decide to use it. Mars Express. Penetrating radars. Well, we're looking for water on Mars. And what about the Earth? What is the biggest problem on this planet? What is the biggest causes of wars in the history of mankind? Lack of water, control of water. You don't need to put these radars on a satellite. You just put it on a blimp, on a piccolo dirigibile. You put it on a helicopter. It's a mission that costs you not hundreds of millions. It costs you hundreds of thousands of dollars. United Nations, UNESCO, has budgets much bigger than that. They should use this technique to go looking for water reservoirs in all the arid zones of the Earth. It's simple, and it's cheap, and it works. We do it for science. Why don't we do it for mankind? Or, Smart One. What has Smart One done for humanity? Well, okay, the little camera. This may be useful for military purposes, or may be useful for many other things. But one of the devices that we tested successfully was high-frequency communication with laser beams. Communication nowadays is the name of the game. Without communication, it seems that we are dead, right? Can you survive more than 2 hours without looking at your telephone, your iPod, or your BlackBerry? No. You got to check your email, right? So what we need today most, it's bit rate. If you do telecommunication with pulse laser, you increase dramatically the bit rate of your life. So this is the way to go for telecommunications. It does work. We test it. Okay? Let's see what Venus Express and Mars Express can do for us. Well, the greenhouse effect, I think it's something that has practical applications today. So when, through studying Venus and studying Mars, we understand the two boundary conditions of a runaway greenhouse effect, I think that these theories can be then applied, at least to convince the politicians that global warming does exist. Okay? Or the understanding of space weather. I told you all the possible applications and all the possible disturbances that we had in our life, that we have continuous in our life because of solar flares. Okay, this is as far as robotic exploration is concerned. Cesare asked me to touch base also on the human exploration, so very briefly, I will express a few biased, I inform you, these are biased ideas. I'm a great supporter of robotic exploration of space. I don't believe that human beings are very useful out there, but let me try to be, at least to express to you my ideas. Okay, 40 years have gone by from the first landing on the moon. And you probably remember the famous sentence. I translated from English in Italian, and when I translate it back in English, it will sound different than the original sentence. But it's something like, a small step for a man and a gigantic leap for mankind, or something like that. So this is what Neil Armstrong said while he was stepping down the ladder from the landing device on the moon. I mean, probably they had studied that sentence for 3 years before he said that, but anyhow, he took his little piece of paper and he pronounced it. Or maybe he had written, like in school, you know, now on the glove of his thing. But anyhow, is that really so? Was it really a gigantic leap for mankind or humankind sending astronauts to the moon? Well, I don't know. I'm not completely sure, honestly speaking. But anyhow, let's see how we reached that point. You remember why the Olympic Games, the Olympiads, as they called it, were played at the time of ancient Greek. It was a moment of peace. All the activities stopped, and the different Greek cities were basically transferring their political aggressivity in the field of sport. It was sometimes very violent sport because there was a lot of politics, despite of what we say in the Olympic Games of the past. So the exploration of the moon was a kind of modern Olympic Games. Nobody after World War II wanted to enter in another war again, but still we had the enemies, the Americans and the Russians and the Americans, and the Europeans were in between like idiots. And what happened? Instead of making World War III, thank God, they moved up their aggressivity to a space war. They wanted to go to the moon first. They wanted to demonstrate to the others that their technology was better, more powerful. So it was like flexing muscles, you know, when you are a child saying, my dad is stronger than yours. No, mine is stronger. You know, it was kind of a childish behavior, but at least it preserved this planet from going to World War III for a long time. And on top of that, there was a gigantic investment in technology. So as you see, technology for space has fallout on everyday life. So from that point of view, that exploration was very good. It didn't allow World War III, and it developed a lot of technologies. But Is that the only way? Well, this is a budget of NASA at the time of the moon exploration and more or less in modern times. In absolute dollars, I mean, if we compare just numeric dollars, the budget of NASA at the time and the budget of NASA today was more or less the same. It's about $20 billion a year, something like that, roughly speaking. The problem is the percentage of the national budget that is totally different, because at the time of the lunar exploration, the US government was investing 5% of the GNP of the United States in the exploration of the moon. Today, they are down about 0.5, 0.6%, depending on the years. Maybe next year will be 0.4 because of the crisis and the budget cuts. So, what that meant? It meant that during that glorious or incredible time that went from 62 to 68, basically, one of the largest slices of the federal budget was invested in research and technology. Wow. Is that good? Well, certainly it's fantastic. And I believe, I'm really convinced, that the technology edge of the United States still today has foundations in that 5% of the GNP that every year for 6 years was invested in the United States. And that did not happen in Japan, did not happen in Europe. It maybe happened in Soviet Union, but it was such a closed system. Soviet Union was really an isolated system that the rest of humanity really didn't see any benefit from that. But if United States today are still the leading country, it's not because of the army. It's because of the technology that they have developed and they continue to develop. This is the real weapon to control the world: technology, research, education. So it's still happening today. Not so much. However, this technology manifested in an incredible number of missions. Automatic mission first, robotic mission first, propedeutic to the exploration of man exploration. And there is also a sociological difference. Nowadays, we make one mission with one budget. We fail, we don't get the budget anymore. At that time, so we must build spacecraft which are incredibly redundant and must have 99.9% of reliability, because otherwise we're fired. We lose everything. At the time of the lunar exploration, instead of increasing the reliability of the spacecraft, they increased the number of spacecraft. I lose one, who cares? I have 5 more. And I think it's better at the time. It keeps many more engineers active than today. And those engineers were working for peaceful purposes instead of, nowadays, most of the technology in the United States is developed no more by NASA, National Science Foundation. It's developed by DoD, Department of Defense. And it's not for everybody. It comes into the society, in the civil society, 20, 30, 40 years later. So it's not as effective as a gigantic exploration program like the one of the exploration of the moon. But however, in any society, you cannot keep up with that pace if at the same time the political evolution, the political situation evolves, and you want to do many other things. And so basically what happened is that the exploration of the moon was like an athlete that was running a marathon at the speed of an athlete that runs 1,500 meters. So you cannot keep up forever. At a certain moment, your heart breaks. And what happened is, in Soviet Union, the society broke, okay. But in the United States, they realized that it was too much for the new requirements of the US society. So basically, and the motivation, the Cold War motivation, was no longer there. So the budget went down. Is it going down to a cruise speed, or is it going too down? Well, my personal interpretation is that despite the fact that NASA has a factor 8 bigger budget than Europe, that doesn't mean that it's too much. I don't think it's enough. In any country, technological investment in education, investment in research and development are never enough. In Europe, and in particular in Italy, we are becoming a third world country. When the investment in research and development goes down 2%, goes below 2%, like in Italy today, these are percentages of investment of a third world country. This is the real issue. And we'll pay the consequences, not now. Because now we are harvesting on investment of 30 years ago. So in 30 years from now, this country, if we continue like this, it will become a technological colony of anybody else, even of Tanganyika. Okay? So we have to look for motivation everywhere in the world to increase the investment in research and development. But this motivation must be serious. There's a little polemic with the space station. 150 billion, if I'm correct me if I'm wrong, maybe even more, have been invested in the construction of the space station. Is that really useful? Is that the real program that keeps everybody going? Honestly not. To the point that even NASA nowadays is using Russian launches just to keep the space program on. But that demonstrates a lack of political interest in the space station. So we're dragging on with these things simply because it would be too embarrassing to say we don't know what to do with it. So the other side of the medal in research and development is that it has to be done with a lot of grano salis, with a lot of intelligence, and creating real motivations, real long-term motivations. Now, can we imagine a world where the only research and development deals with space exploration? Well, it sounds a bit funny because we need research and development in biochemistry, in biology, in medicine, and so on and so on. So the question could be, if we need 1,000 times more than the expense of the space station to make a colony on the moon, on Mars, it means that the exploration by astronauts on Mars will never take place, because the only condition to do it is to have one single investment in space technology and development, which is unthinkable. Consequently, where can we find a budget by maintaining the other budgets for research and development for the other disciplines? Well, my only hope is that one day peace will explode, and if peace explodes, all the deficits of this world will be solved immediately. Think how much we spend in Afghanistan and in Iraq cumulative every day. You know how much is it? United States carries 90% of the expenses, but there is also the rest of the world. So we spend something like 3 billion a day in these two worlds, which means that in 1 year we wouldn't have a big budget problem anymore. Okay? So maybe that is the source of funding for the future. So maybe landing on Mars one day for human beings will be just the results of peace in the world. I don't know. It's a question. Maybe it's a hope. Thank you for your attention.
Se non ci sono domande, allora ringraziamo di nuovo il dottor Coradini per la sua presenza e per la bellissima conferenza.
Mi scuso ancora del ritardo.
No, tutto. Bene, grazie allora e buona serata.